So let's begin the study of field extensions or extension fields. A field K containing another field F is called a field extension. So if K is a field that contains a field F as a subfield, we say that K is an extension field of F. We use the shorthand K over F. K slash F, let's read it. It's not a division in any sense. K slash F is a field extension, we say. That means simply that K is a field that contains another field, little f, capital F. Example would be, we saw, this contains rational numbers. Real numbers contain that. Complex numbers contain real number. You could take, stuff like that. More generally, we saw things like, if you take fx, okay, so f is a field, and this is an irreducible polynomial, then this is a field that contains f, this guy. If that notation is confusing, let's write k equal to, well, this is an irreducible polynomial, then this is a field extension. And these are the kind of field extensions that we are mostly going to be interested in. This one gets an asterisk marks. In fact, these two are both examples of that sort of extension. But this one is not quite, really. We want to make a sense of when two extensions are the same. So we say, and I have a notion of isomorphism of field extensions. We say two extensions, continuing with the definition, extensions are isomorphic if there is a field isomorphism phi from k to k prime whose restriction to f, you see f sits in both k and k prime. It is just identity of f. So you have k and k prime both containing f. Phi is an isomorphism. When you restrict to f, you just get identity. That's when we say two extensions are isomorphic. And when you have three things, like L, K, M, then we say it's a tower of extension, etc. I have a few more definitions, but maybe just to digest this, let me just say quickly, why are we studying field extensions? So the examples that you want to keep in mind are things like this that we saw last time. So this is a field that is an extension, and if you take alpha to be the image of x in K, the coset of x, then alpha square is 2, after you have identified Q inside K. So Q sits inside K via identifying a number like 3 with the coset of 3 plus the coset of 3, And if you take alpha to be the image of x, then alpha square is 2, and indeed k is really all expressions of the form. Elements of k can be uniquely expressed as a plus b alpha, where a and b are rational numbers. This is just obtained by adding the square root of 2 called alpha to rational numbers. So the study of extension fields really stem from trying to solve polynomial equations. And when you find that some equation does not have a root in Q, but we built this field K, but does have a root in this extension field. So by slightly increasing the set, slightly growing the set to a slightly bigger field, I have now solution of this polynomial equation. And now you can see what other equation you can solve in this field. An extreme example of this is when you construct another extension like this. X squared plus 1 cannot be solved in real numbers. So this is a irreducible polynomial because x squared plus 1 is always positive over real numbers. So if you quotient by that ideal, that's a field. Now in this field, if you call alpha to be the image of x, then alpha squared plus 1 is 0. So alpha square is negative 1. And indeed, you can check that this is isomorphic to C. So this extension field, this now contains real numbers. And all elements of this field just look like A plus B alpha, A, B real numbers. And this is really C. This alpha is really what we call I abstractly. Usually this alpha is called an I. So the way you get complex numbers is exactly one of these constructions. By taking one variable polynomial ring and quotient, forcing this relation that alpha squared plus 1 equal to 0 by quotienting out by the polynomial x squared plus 1. And indeed, you see every complex number is a real number plus a real number times the square root of minus 1. And now, in this bigger field, the equation x squared plus 1 has a solution, namely alpha, and minus alpha, in fact. So x squared plus 1 factorizes in this bigger field as x plus alpha times x minus alpha, because alpha squared is minus 1. So this polynomial has a solution, in this bigger field. Now you can ask what other polynomial does. So if you had to introduce a new field for solving every polynomial equation, that would be sort of useless. But you could now ask what other polynomial can be solved in this bigger field. In this example, K is really complex numbers. Then in this case, we have the most wonderful theorem called the fundamental theorem of algebra. And it says that once you do this, every polynomial with real coefficients, in fact every polynomial with coefficients in K can be solved. Every polynomial with coefficients in Kx has a solution in K itself. You don't have to extend anymore. You just had to add this I, and now for free you get solutions of all polynomial equations. So such facts is what makes the study of extension fields very, very, very useful and interesting. So I'll give you a few more definitions and then we'll start proving things about extension fields next time. So we have field extension, just means one field contained in another field. Sometimes we draw it like this. Simply means that, the other way around. Simply means this, that K contains F. And when you have like three things, a F contained in a K, contained in a M, three fields like that, we call it a tower of extensions. Okay. And we say that this is a sub-extension. We say K over F is a sub-extension of the bigger extension. You have one big extension and here is a sub-extension. Okay, that's just some language. Now the first important observation, and this is why we reviewed vector spaces before starting field theory, is that if K over F is a field extension, we'll just say extension, because that's the only kind of extension we are studying. If this is an extension, then K is a F vector space. I mean a vector space over F. You could say K becomes. Well, K of course is an abelian group. There is a plus. What is the scalar multiplication? If you give me a alpha from F and K from K, then alpha times K just means the product of alpha and K in the big field K. After all, F is a subset of K, so alpha still lives in capital K. And capital K is a field, so it has a multiplication. So this multiplication makes sense. And then you check that the vector space axioms hold. So K becomes a vector space over F. Just like complex numbers, this is a vector space over real numbers. It's really just the two-dimensional vector space, right? You can write these as A plus B times I. And so identify that with the pair A comma B. That gives you a two-dimensional vector space. So this is isomorphic to R2. For example, here, this is isomorphic to Q2 as a vector space. Yeah. We are going to be mainly interested in the situation when this vector space is a finite dimensional vector space. And those are called finite extensions. The dimension of this vector space, so here's the definition, that K colon F denote the dimension of this vector space. Dimension of K as a F vector space. Dimension of K as a F vector space. And this is called the degree of the extension K over F. So both these have degree 2. This is a degree 2 extension. This is also a degree 2 extension. Okay. And we say that an extension is a finite extension if this degree is finite. This degree is finite. So you don't have to go too high to solve, so that the extension is not too big. That's sort of the meaning. So the theorem that we are going towards is that if you take a irreducible polynomial, any non-constant polynomial, this is a field, then there is a finite extension where this polynomial has a root. Then there exists a finite extension K over F such that P has a solution in